Hi, my name is Mio Shosh, and today I'll be presenting to you my Physics 2212 Lab 4 circuits. So a little introduction. The purpose of this lab was to apply the energy and current conservation laws to predict how current circuits behave. We used multimeters to measure current and voltage, and we explored how capacitors work by observing their charging and discharging processes. A preview of our main results. We confirmed our assumptions of the loop rule that the sum of the voltage changes in our system equals 0. So moving forward, here are some of our fundamental physics principles that we used. We have Ohm's law, as we all know, the different variations of it, and then Kirchhoff's junction law, which is the total current entering a junction equals the total current leaving, and then Kirchhoff's loop law, which states that in a closed circuit, the sum of the voltage drops around the loop is 0. So our experimental setup, we have our system, which are the batteries, the wires, multimeters, and resistors, the surroundings, which is the environment, which is the table, the rest of the room, and general earth. And then when the circuit is open, the ammeters readings start at 0 amps, so there's no current flow. Numbers shown here aren't correct, but they are straight out of the lab instructions. So here are the setup and observations for the first experiment. We have two 1.5 volt batteries in the series, the resistors, and then the two ammeters to measure the currents, I1 and I2. Our assumption is that I1 minus I2 equals 0, meaning the two currents should be equal in opposite directions. And then the simulation instructions were stated that we should set the battery voltage to the same thing, 1.5 volts, and ensure that the ammeters are connected properly to read positive values. And here's a picture of our experiment. So a little bit about our results. So our readings were about negative 38 to negative 40 milliamps with the ammeter, and then when we flipped it, we had pretty much exactly the same numbers. Same thing with the voltmeter, and this confirmed that I1 minus I2 equals 0. And the reason why is because the voltmeter's high resistance blocks the current, resulting in 0 current flow. So experimental setup 2, we have our system, which are the batteries, the wires, capacitor, and light bulb. Surroundings are, once again, table, rest of the room. And then the initial conditions was that we have the circuit open with no current flows, and the capacitor actually holds no charge. So our observations was that with the battery connected, the light bulb started bright, but it dimmed gradually over time. With the capacitor connected, the light bulb was initially bright, and then it dimmed much slower as time passes. And then while charging the capacitor, the conventional current flows from the light bulb to the resistor. And then when the capacitor was discharging, the conventional current flows from the resistor back to the light bulb. Here's a bit more about the detailed results from experiment 2. So about the brightness, the light was really bright when it was powered directly. It was less bright when we used the capacitor, and as the capacitor charged, the light gradually dimmed. The current decreased over time and eventually dropped to 0. And then our timing observations, we recorded up to 1 minute 30 seconds, and the initial voltage was at 7.9 volts, and it stayed very stable the whole time. And it was the same situation for the second trial. So assumptions, sources of error. Assumptions we knew the battery's initial charge, that the multimeters provide accurate measurements, and resistance values printed on the light bulbs were correct, and then the resistance of the wires are negligible. And then we had some human error or data insufficiency, which could have led to other sources of error. So a little discussion. What if you were doing this lab in real life and used an actual ammeter instead of ideal simulated ammeter? What difference about a real ammeter, and how would it affect the circuits you hooked it up to? So since the lab was used real circuits, the first part of the question isn't really relevant. So in practice, the capacitor won't charge instantly as predicted, and this delay happens because of the internal resistance present in both the battery and capacitor, which creates equivalent resistance in the circuit. Number 2, if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Once again, since the lab was conducted with real circuits, the first part doesn't really apply. And the virtual ammeter acts kind of differently because it has no resistance, whereas the real one has a small resistance, and this allows the virtual ammeter to give more precise current readings, making the loop rule accurate.